This next lesson will be about mass spectrometry. I'm going to share my screen. Okay, the importance of mass spectrometry is that it enables us to determine the molecular weight and sometimes the molecular formula. It uses a very small sample. It is fundamentally different from spectroscopy because it does destroy the sample. The sample cannot be recovered. Mass spectrometry uses a beam of high energy electrons to break a molecule apart. Right, this is like shooting clay pigeons or clay targets. The electrons strike the molecule and cause it to fragment. Okay, here's a very simple electron impact reaction. The electron strikes methane. It ejects one of the electrons, and that produces what is called a radical cation. So there's an unpaired electron, there's also a plus charge. Okay, here's an electron impacting ethane. Okay, so that gives the molecular ion, that's just ethane minus an electron. And we can also get an ethyl cation. Okay, when this hydrogen atom breaks off. Okay, most mass spectrometers will just be able to detect those fragments that have the positive charge. Okay, so the methyl radical will not be detected, but we'll see the methyl cation at mass to charge 15. Okay, there are several designs of mass spectrometers. This is the magnetic sector. And here we have a probe where we put the sample. We heat it up. This is under very high vacuum. And so the sample is swept into the gas phase, and it's shot with electrons. The fragments then go through these slits, and those ions that are too heavy, okay, won't reach the detector because they'll run into this side of the tunnel. Those that are too light will collide with this side of the tunnel, and those that are just right will follow this pathway and reach the detector. The most common mass spectrometer separates ions by magnetic deflection. A mixture of ions is accelerated and passes through a magnetic field where the paths of the lighter ions are bent more than those of the heavier ions. By varying the magnetic field, the spectrometer plots the abundance of ions of each mass. The exact radius of curvature of an ion's path depends on its mass to charge ratio, symbolized by m/z. In this expression, m is the mass of the ion in atomic mass units. Z is the charge. Z is almost always +1. Okay, so here is a mass spectrum. This is for 2,4-dimethylpentane. This molecule has a molecular weight of 100. So this is the molecular ion peak, okay, where just one electron has been knocked loose. Okay, the difference here between 100 and 85 is 15, so that means we've lost a methyl group. And then 57 would be a tert-butyl cation. 43 would be an isopropyl cation. Okay, and then the y-axis is the relative abundance. So whatever the most abundant ion is, it's set to 100%, and everything else is relative to it. Okay, we have a GC mass spec. This is often used in forensics and environmental analysis. Okay, this first separates compounds, and then each compound is then subjected to mass spectrometry. Okay, so different compounds will travel at different rates through this column using a carrier gas of high purity helium. Right, in high resolution mass spectrometry, okay, which we don't have here at Emporia State, but masses are measured to a very high accuracy of about 1 part in 20,000. And where that's important is if we look at a low resolution mass spec and we get a mass of 44, okay, that could be any one of these 4 compounds. It could be propane, C2H4O, it could be CO2, it could be this. But using high resolution mass spectrometry, we can see that there are differences among these 4 compounds. Okay, if we go out to enough decimal places. Okay, this is where mass spectrometry is really useful, and that is looking at isotopes. Okay, so these are masses of some common isotopes: carbon-12, hydrogen-1, oxygen-16, nitrogen-14. And isotopes are present in their usual abundance. Okay, so carbon has a carbon-13 isotope present in 1.1% abundance. The rest is carbon-12. And so we'll see a small, what we call M+1 peak as a result of the carbon-13 naturally occurring. Another example is bromine has 2 isotopes in nature, 79 and 81, and they have almost equal abundance. And so we'll see 2 peaks, an M and what's called an M+2 peak, that are almost equal in height. Okay, here are some isotopes of some common elements. Okay, most nitrogen is nitrogen-14. There's just a very little bit of nitrogen-15 in nature. Sulfur does have measurable amounts of 33 and 34. Okay, chlorine has 2 abundant isotopes, 35 and 37, and they're in about a 3-to-1 ratio. Okay, bromine, we said, had 2 isotopes in nature that are in about a 1-to-1 ratio. For iodine, the only stable naturally occurring isotope is 127. It's 100%. Okay, so one of the ways we can deduce iodine is, first of all, if we have a high molecular weight, or we see a loss of mass of 127, that would imply iodine. Right, so here is 1-bromopropane. Okay, here you can very clearly see the bromine signature. Okay, this peak is from bromine 79. This peak 2 units greater is from bromine 81. Okay, and so we have loss of 15 here. That's loss of a methyl. We still see the bromine signature. Okay, so we've lost a methyl from this side. And okay, 43 would be the propyl. Okay, so we've lost lost the bromine atom here. And this likely will rearrange to an isopropyl. Okay, so here's 2-chloropropane. Okay, the isotope signature is distinctly different from that of bromine. Here the M and the M+2 peak are in about a 3-to-1 ratio. And we can see with this set of peaks, we still have the chlorine atom present. Okay, we've lost a methyl, loss of 15. And again, 43 would be the isopropyl cation, where we lose a chlorine. Right, here's a compound that contains sulfur. Okay, here's sulfur 32, 33, and 34. Okay, here's normal hexane. Okay, there's the common fragmentation pattern here is loss of methyl, then CH2, 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 and so on. Okay, so this has a molecular weight of 86. This is loss of 15, loss of a methyl. Okay, here we have loss of 29, loss of an ethyl. Loss of 33, which is loss of a propyl. And then we see the peak from the ethyl cation. Okay, so if hexane fragments this way, okay, we see the butyl cation at 57, but the ethyl radical, which is what breaks off, is not observed. Okay, so what we look for is the difference in mass between those peaks. Okay, you can also fragment this way, where an ethyl cation breaks off. We see a peak at 29, which is detected, but we don't see the butyl radical. Right, here's the mass spectrum of 2-methylpentane. We often see fragmentation at branch points because, of course, secondary and tertiary carbocations are more stable. Okay, so this peak at 43, that's our isopropyl cation, where the propyl radical is broken off. Okay, 86 minus 71, that's a loss of 15, so that's a methyl group breaking off one of the ends here. Okay, so fragmentation occurs more often at branch points. Okay, a couple different fragmentation pathways. This is the 2-pentyl cation, okay, where it breaks here, and this is the isopropyl cation where it breaks here. Resonance stabilized cations tend to be very abundant. Okay, so here, if we fragment at this position, we get an allylic cation, okay, in which the plus charge is delocalized by resonance. And these resonance stabilized cations, again, tend to be very abundant. Okay, and here's a good example. This is trans-hex-2-ene. Okay, this major peak here at 59 is from this methylyl resonance stabilized cation. Okay, 84 is the molecular ion peak. We've just lost an electron. Here's the benzylic cation. Okay, it's very probable to have fragmentation occur on the side chain between the first and second carbon. That produces this very stable benzylic cation. Okay, if we have an alcohol, one possible fragmentation pathway is loss of water. Okay, so if you see a difference of 18 between the molecular ion peak and the next peak, okay, that probably indicates loss of water. You probably have an alcohol. Another common fragmentation pathway is what we call alpha cleavage, okay, where this carbon-carbon bond breaks just right after the CO bond, okay, because again, that gives us this resonance stabilized ion. Okay, so here is 3-methylbutan-1-ol. Loss of water occurs so quickly that we actually don't even see the molecular ion peak. So we have an M-18, which would indicate loss of water. And 55 is the base peak. Okay, that's a result of this. Base peak is the largest peak. That's a result of this resonance stabilized ion. Okay, when you lose water, of course, you get an alkene. Okay,